Hello and welcome to our channel. In this video, I'll be solving this question of differential calculus using two methods. One will be conceptual method using a little bit of graph, and the second one is going to be more sophisticated. So let's start with the question. The question says that find all twice continuously differentiable function f defined from r to 0 to infinity, satisfying the condition for every x belonging to r. How we are going to solve the question? First of all, I'm going to start with the condition that they have given. See, two things I have highlighted. The function is taking the positive value, and second, the condition that they have given us. I'm rewriting this condition as f double dash of x multiplied by f of x minus 2 into f dash of x is greater than or equal to 0. First of all, what I'm going to do is I'll try to rewrite the left-hand side of the function as the derivative of some function. And that requires a little manipulation. So I'm multiplying and dividing it with f of x. If you multiply and divide it with f of x, you will get upon f of x greater than or equal to 0. Still, it is not the exact derivative. So I'm doing a little bit more manipulation, multiplying and dividing it with f cube of x. Now you can see that f cube of x, along with that, if you connect it with the quotient rule of derivative, you can rewrite it as d by dx of f dash of x upon f square of x greater than or equal to 0. So using the quotient rule, I have rewritten this encircled term as the derivative of f dash upon f square. But f dash upon f square is once again a derivative of some function. Which function? I can rewrite it as d by dx of minus 1 upon fx. So by observing the expression, we have written that this is equals to the derivative of minus 1 upon fx. In the next step, f cube x, because it is given as a positive valued function, I'll merge it with 0. I'll cross multiply and merge it with 0, and we'll rewrite the inequality as d2 upon dx square minus 1 upon fx. In fact, let us remove this negative sign also here or adjust it with the inequality. So I'll write d2 by dx square of 1 upon fx. Adjusting the sign in the inequality gives me less than or equals to 0. I'm writing it as the first inequality, or I'm going to mark it as first. Why? Because this is going to be important relation that I will be using for identifying all functions satisfying the conditions of the question. So whether it is method 2 or method 1, I'll be using this first equation or inequality. Now let us continue with method 1. So after deriving this first relation, I'm going for method 1, in which from the first equation, I'm interpreting that 1 upon fx has a second order derivative negative or 0, which indicates that the graph of the function, if it has concavity, it will be concave down. If the function is concave down, then you can say that rough sketch of 1 upon fx is going to be something like concavity downwards and defined for every x belonging to R. If it is concave down and is defined for every x belonging to R, then 100% you are going to get some portion of the graph below x-axis. But some portion of graph below x-axis says that fx has now become a negative value function. But if x cannot take negative value means here we are getting a contradiction. Contradiction in the sense that function have a concavity downwards and it has a negative value. No, it's not possible according to the conditions given in the question. So I rejected this case. So I have rejected the case that fx has a concavity or 1 upon fx has a concave down graph. Now what we can interpret? If it is not concave down, then only possibility that we have is equation 1, or you can say inequality 1 should be satisfied and function has to be positive. Then this is possible only when the graph of the function is like this, or you can say that 1 upon fx is a constant function. If you take 1 upon fx as a constant function, positive side I'll take the values. So function is taking positive values means fx positive, so 1 upon fx will also be positive. And at the same time, 1 upon fx must be a constant function. 1 upon fx constant means fx will also be a positive constant function. If it is positive constant function, then its f dash and f double dash both are going to be 0. If both are going to be 0, then I can say that both the conditions, one, the function needs to be positive, and second, the inequality given in the question, both will be satisfied. So we have the answer. We have identified the function satisfying all the conditions given in the question as positive constant functions. So using method 1, we have proved this, or in fact, we have derived or we have identified the kind of function. Now let us see how we are going to derive the same result using method 2. What we are going to do in method 2 is, I'm going to rewrite the relation 1 once again. So in method 2 also I'm using the same relation, that second order derivative of the function 1 upon f of x is less than equal to 0. If it is less than or equals to 0, then for method 2, I'm taking a new function g of x as 1 upon fx. But if you're taking 1 upon fx as g of x, then this inequality can be written as g double dash of x less than equal to 0, which indicates that g of x has a concavity downwards. Now concavity downwards means you can say that g dash is going to be decreasing. If g dash is decreasing, then how I'm going to use it for the question? Let us see. I'll take two arbitrary real numbers a and b, assuming a to be less than b. Further, I'll take another real number u less than a, and the next real number v greater than b. Okay. I'll join these points. That means all these points are corresponding points on the graph of the function g of x also I'm taking. So let me explain it with the help of a graph a little bit. Let this be the graph of the function, and the corresponding points I'm just marking. Let this be a and b, and in fact let me take this one as u. So I'll take this as u, this is a, then greater than a we have taken b, greater than b we have taken b. Marking the corresponding points on the graph ABCD. From the concavity of the graph, it is very much clear that slope of the line joining AB is going to be more than the slope of BC, and BC ka slope is going to be more than that of CD. They can be equal also because of the equality sign over here. But yes, I will write that these slopes are in this particular order. So let's write it mathematically now, starting with the slope of AB, which can be written as G of A minus g of u upon a minus u. It is going to be greater than or equals to g of b minus g of a upon b minus a, which is going to be greater than or equals to g of v minus g of b whole divided by v minus b. Next what? Because all the g values are positive. Why they are positive? Because I have assumed g of x as 1 upon fx, and in the question fx is positive. So what I'm going to do now, observe carefully how I'm writing, because g of u and g of v are also positive. That's why I can write that g of a upon a minus u is greater than or equals to g of a minus g of u upon a minus u is greater than or equals to g of b minus g of a upon b minus a is greater than or equals to g of v minus g of b upon v minus b is greater than or equals to. So this is also greater than or equals to minus g of b upon v minus b. Okay. Further, now I'm writing it as g of a upon a minus u is greater than or equals to g of b minus g of a upon b minus u, b minus a is greater than or equals to minus g of b upon b minus b. So I just compared their slopes and have written it like this. Now u and v ko I'll take like this. U is tending towards minus infinity and v is tending towards plus infinity. Taking limit all the three sides, putting u as minus infinite and v as plus infinity, what we are going to get on the extreme left side is 0. Middle term is not going to change because neither a nor v is there. So we are going to write it like this. and this is greater than or equals to 0. So after putting the limits, this is what the inequality says. But from this inequality, again, I can conclude that g of b minus g of a is turning out to be 0. But if it is turning out to be 0, what do you mean by this? It means that we are getting g of a is equals to g of b for any pair of real numbers a and b. Since it is true for any real a and b, whatever a and b are taking, I can say that this implies g of x must be a constant function. If g of x is a constant function, means 1 upon fx is a constant function. And since 1 upon fx is a constant function, so definitely I can say that fx is a constant function. And further, fx is also taking the positive values according to the question. That's why the only function satisfying all the conditions given in the question will be positive constant function. So see, we have proved it using another method as well. Positive constant function. Well, this brings to an end to this video. So thanks for watching. Please like the video and subscribe to our channel. Bye-bye for now.